Hello everyone. So today I'm going to talk about our recent work on this human-object interaction using the art signals. So enabling human-object interaction plays a key role in many mobile applications. For example, in the supermarket, if you set the price of your favorite milk gets gross, then you can simply pick it up, use it as a pen to write in the air, showing your disappointment. Similarly, in the library, you can convey your opinion about your favorite book. For example, you can just hold this pen and you hold this book, use it as a pen to write a heart in the air, showing that you love this book. Well, to enable such a sense of human-object interaction, actually, there are two requirements. First, you need to precisely capture the human gestures, hand movements, and your intentions. Second, you need to identify the object you are currently interacting with. Well, the boosting of this computer vision technique made the video analytics a natural choice for such a human-object interacting. However, people showed privacy concerns about this system. Besides, we know that the performance of this video system is highly sensitive to the background noise, especially in our physical stores, supermarkets, our warehouses. During the past, actually millions of RFID tags have been deployed in our physical world, like the warehouses, supermarket. Once these tags are attached to different atoms here, the EPC code of each tag essentially reflects identity of each item. So by recognizing the item, recognizing the RFID tag, we can essentially recognize the tag atom. On the other hand, when people pick up an object for interaction, so the trajectory of the tagged RFID on this atom actually reflects the moving trajectory of your hands and your gestures. So, by tracking the RFID tag attached on each atom, we can actually recover the trajectory of your hand movement. So these millions of RFID tags essentially provide us a basic infrastructure for human-object interaction. Well, to track the RFID tag, the traditional way is to localize the tag at each time point, and then connecting these locations into a trajectory. However, the performance of this tracking scheme is highly sensitive to the number of antennas you use here. For example, as this figure shows, if you just use 4 antennas here, we can see a very large location uncertainty. When you double the number of antennas here, you can see the location uncertainty decreases. Well, as ER racking usually requires centimeter by volt accuracy, so we need to add more and more antennas, which will finally result in an antenna crisis problem. So very high deployment cost. Well, to solve this problem, the previous system either optimizing the displacement, optimizing the location of these antennas, or they build up a synthetic actuator. However, this system still requires at least 4 or 8 antennas in function. So here comes the question. Can we build up a single antenna-based tracking system to enable such a sense of human-object interaction? In other words, can we use the existing RFID infrastructures to build up such a human interaction system? So the answer is yes. The basic idea here is to replace those burdensome cost RFID antennas with those low-cost, small form factor RFID tags. So by tracking the RFID tag array, we can essentially tracking the hand gestures and hand movements. However, to put this simple idea into practice, there are two challenges. The first challenge is the low per tag reading rate. We know the tag reading rate is critical to the performance of tracking algorithm. However, as we attach multiple tags on each atom, the tag reading rate will decrease. This is because RFID abides by the floated aloha protocol. So more tags in front, the more collisions and RF traffic. So the tag reading rate will decrease significantly. Even worse, we know in our physical world, usually we see a lot of atoms in front. So if we attach multiple tags in each atom, then the tag reading rate will decrease significantly. While the second challenge is the inductive popping effect. As we mentioned before, So as we mentioned before, more tags here, the lower location ambiguity we will have. However, if we put multiple tags per atom, due to the limited space of the atom surface, then the distance between adjacent tags will reduce, which will finally result in such a tag calming effect. As a result, the phase readings and RSSI readings will be highly affected. To solve these two challenges, here we propose Pantomime. So Pantomime is actually a single antenna-based RFID tracking system, which only requires 2 tags per atom. It works with commercial off-the-shelf RFID devices without any hardware modifications. So let's first look at how to address the low tag reading rate problem. So our basic idea here is to send those target tags that the human is currently interacting with, and then stopping other tags from replying. So the first problem here is how to send those target tags. It is based on such an observation. Actually, when humans interact with an object, they will pick up this object first, which will result in a displacement of the tags on this atom. So by observing the phase readings of each tag, we can actually send those tags with whose RF phase will change significantly. So these tags are the target tags. In contrast, those non-target tags, since there is no displacement, so we can distinguish them from those target tags easily. So after finding those target tags, the next step is to boosting the reading rate of these target tags. To achieve this goal, we are actually blocking those non-target tags from replying. So how to achieve this goal? Here, we dive into the C1 Gen 2 protocol. Actually, at the beginning of each inventory round, the reader will send the select command, indicating which tags it wants to interrogate with. Notice that at each inventory round, we actually set the tag mask to those target tags. So, only those target tags will enter this ready state and reply in the following frames. By doing so, we actually reduce RF traffic and collisions, so improving the tag reading rate. So after boosting the tag reading rate, the next step is to tracking the tag atom. The basic idea here is to, instead of tracking this tag atom directly, we are actually inversely tracking the relative movement of this antenna in the frame of the reference of the tag array. As this figure shows, when the tag atom moves from the position 1 to the position 2, then in the frame of the reference of this tag array, it is similar to move the tags move the antenna from the virtual position 1 to this virtual position 2. To track this virtual position, actually here we also employ the phase readings. So the phase actually reflects the distance between the tag and the antenna. So by intersecting the pseudo distance from each tag to the antenna, we can actually determine the location of the antenna. So by tracking the antenna in the frame of the reference of the tag array step by step, then we can recover the virtual trajectory of this antenna. Then, by rotating this trajectory 180 degrees, we can finally get the trajectory of the atom, so the human gestures. So this figure shows the results recovered by our pseudo-arrangement algorithm. We can see the lighter U. The shape of this lighter U is well preserved except for some disconnections. This is due to the fact that the location estimate is computed independently along the timeline. Well, to smooth this result, here we further introduce position velocity model to constrain the movement of hand. Then we use the hand information to constrain the moving direction of your atom. Finally, we incorporate this model and the previous pseudo-arrangement algorithm using the EKF model. So here I will not go into the details of this EKF and refer our audience to check our paper for more details. So we implement Pantomime with the commercial off-the-shelf RFID devices, and we test our system in multipath prevalent environment. Here we attach different number of tags on each atom. So here I show a demo to illustrate how the Pantomime works. In this demo, actually I attach 2 tags on the atom and use this atom to write a purge. So you can see the recovered trajectory is also well preserved and can easily distinguish. So apart from this live demo, we also conduct 2 real-world case studies. So first case study is about the writing in the whiteboard. Here, we attach 2 tags on the pen and ask the user to write letters and words on the whiteboard. Then, our Pantomime recovers the trajectory of these writing letters. You can see here the letter V is also well preserved. On the case study 2, we actually conduct the radial store atom query. So in each case study, we attach different number of tags on each atom. Then we design several gestures and ask the user to perform this gesture to convey their opinion about this atom. As you can see here, even the users writing on the 3-dimensional space, we can see the recovered trajectory is also well preserved. So summary. So Pantomime is actually the first single antenna-based RFID tracking system which can enable people writing in the air or on the whiteboard or for the human-object interaction. So the basic idea behind is to replace those burdensome, costly RFID antennas with those low-cost, small form factor RFID tags. So for our future work, we plan to make it work in multi-user case and enable it to work in 3-dimensional space. So that's all for my presentation, and I'm happy to take any questions.